Hi, in this video we are going to be discussing the tutorial 6 on cache. So what is cache? Okay, so looking back at your lecture slides, you have a very good idea that when a processor executes instructions, the bottleneck is always the access to the external memory. Okay, so whenever a processor needs to access external memory, either instruction or data, it is really slowed down because memory access has not improved as significantly as the processor speed over the years in terms of technology. Okay, so that is why the cache plays an important part, and what the cache tries to do is it tries to keep instructions and data that are regularly accessed within the processor space itself, okay, so that we minimize the access to the external memory. Okay, so that is where spatial locality and temporal locality play a part. Okay, so of course the details are in the lecture slides, so with that understanding, let's start with the first question. So in the first question, we have a direct map cache, okay, with 16 one-word blocks that is initially empty. Okay, so given any cache question, the first thing that we must always do is we are given a statement, okay, on how the cache is designed. From there, we should get a visual representation of how it's going to look like. Okay, so for a direct map cache, we know that every address is going to map to a single cache line. Okay, and we are given that we have 16 one-word blocks. Okay, so how do we translate this? So 16 one-word blocks means this 16 is the number, okay, of cache lines. Okay, so if we look here, this is the number of cache lines. Okay, 16. Okay, and in each cache line we have one word. Okay, so this is again, you have to be very careful. How big is one word? Okay, this can be a tricky question, especially in the exam and so on. Okay, because if we just in this question we are given that it's a MIPS processor. So for MIPS processor, we know that one word is 32 bits. Okay, which means you have 4 bytes here. Okay, so of course in the exam or an assessment, it's easy to sort of trick you to say that this is not a MIPS processor, but it's a different type of processor where one word is just 2 bytes, so you have to be very careful to understand the context of this one word. Okay, so in this case we are given it's a MIPS processor, so one word is 4 bytes. Okay, so this will tell us how many byte offset bits we need. Okay, so given this information, we know that for the cache lines we need 4 bits to the power of 4, and here we need, okay, 2 to the power of 2, which is 4 bytes. Okay, so once we have this information, okay, we know that 2 bits for the byte offset and 4 bits for the cache line index. Okay, so that is where we have this. Okay, so this representation on the 32 bits, okay, broken up into the tag, index, and offset, this is very important. Okay, so once we have this, we know that how to interpret any given 32-bit address to figure out where it gets mapped to. Okay, so let's look at the first access. So the first access is memory address 4. So all I need to do is figure out the tag, index, and offset. Okay, so what I see that it points to line 1. Okay, and then since initially it is empty, okay, so I change the valid bit to 1, update the tag, and put the memory information here and the data over here. And same thing. Okay, if I look at second memory access, it points to line 4. So again, the valid bit is 0. Okay, so if you change the valid bit to 1, update the tag, and put the data here. Okay, so if you recall the process, whenever a memory access comes, what I will do is I will check the uh, cache line index. Okay, so it will point to a particular line, and in that I must go and check this valid bit. Okay, if the valid bit is 0, okay, then the cache line is currently empty. So what I need to do is I can take the data that I'm accessing and update it into the cache. So I change the valid bit to 1, take the tag information from here, from the current memory access, put it here, as well as the data and put it here. Okay, similar for the fourth access. Okay, so I'm just going to do this here. Now, at this point of time, you can see that I'm accessing words from memory. Okay, so when I say memory 4 here, I have four, I have the bytes 4, 5, 6, 7 here. Okay, same thing, 16, 17, 18, 19, and so on. Okay, so I'm accessing 4 bytes starting from the memory address given here. Okay, which means that if let's say the fifth access over here was a byte access, okay, to any of the bytes that are already stored here, then it would have been a hit. Okay, then I would have fetched the data from the cache and directly given it back to the processor. Okay, so that is where the cache comes in. Now, let's look at the fifth memory access. In this fifth memory access, we're accessing memory address 80. And what you see is it points to cache line 4. Okay, so the second access also point to cache line 4, and this access also point to cache line 4. Okay, and when I see the valid bit is set, okay, then what do? I need to check the tag that is currently there with the tag of this new memory access, and I see that the tag has a mismatch. Okay, so since the tag is a mismatch, then I need to update the data. So I will put the new tag information and override the old data with the new data, which is from memory 80. Okay, and of course I carry on with the whole process for the remaining memory access. So as long as you understand how this thing works for direct map cache, is quite straightforward. Okay, and this is the final contents of the cache after all the accesses are complete. Okay, so I'll not go through each and every one. Okay, once you go through all the accesses, this is what you should see. Okay, so that is your direct map cache. Okay, let's go on to the next question. The next question is a two-way set associative cache. Okay, so what is the main advantage of a set associative cache? A set associative cache helps us with temporal locality. That means uh, if I'm accessing two different memory locations with different tag information that map to the same cache line, then I can keep both of this data or multiple sets of this data in the cache, okay, without having to continuously keep replacing it. Okay, so this is different from, let's say, going back to this, if let's say instead of having a one word cache line, I increase it to two word cache line. Okay, if I were to increase to multiple words in each cache line for a direct map cache, what I'm actually improving is the spatial locality. Okay, that means when I fetch one data, I'm fetching more data that is beside this current data. Okay, so that is spatial locality. Whereas here, I actually improve the temporal locality. That means I'm accessing different locations that are far apart. Okay, but then they happen to match back to the same cache line. Okay, you have to remember, if I match back to the same cache line, for a direct map cache, I will always have to keep replacing it. Whereas with a set associative cache, I can keep both sets of data side by side. Okay, so that is where the set associative cache comes in. Okay, so again, the first step is, given this line, we must be able to figure out how the cache is going to look like. Okay, so we are given is a two-way set associative. Two-way set associative means I have two sets of data. Okay, so this is one set of data, and this is another set of data. And what's the other information given? You have two word blocks. Okay, that means for each set of data, I have two different tag information, and here I have two word blocks, and here I have another two word block. Okay, so every time I fetch data from memory to the cache, I fetch it two words at a time. Okay, so which means that in one cache set, I have total of 4 words. And since I have a total of 16 words, I have a total of 4 cache sets. Okay, 4 cache sets. So this 4 cache sets gives me 2 bits for the index, and within each cache line that I fetch from memory, I fetch 2 words. Okay, so since it's 2 words, it is 8 bytes. So for 8 bytes, I have 3. Okay, so that is how I come up with the uh, 3 bits offset, 2 bit set index, and 27 bits for the tag. Okay, so once I have this, okay, it's easy for me to fill up the cache based on the accesses that I have. Okay, so maybe just to explain this a bit more. 4 words per set, okay, which is but it is 2 words per access, okay, and 2 words is 8 bytes. Okay, so that is why it's 2 to the power of 3. Okay, over here. So this 4 words per set is the total number of words in one cache set, but we know that every time I fetch data from memory to the cache, it is 2 words at a time. Okay, so for instance, 2 words at a time is 8 bytes, so it is 3 bits for the byte offset. Okay, so just to make this part clear, okay, well, how I get the 3 and 2 over here. Now, if I look at the first memory access is address 4. Okay, so you have to always remember that now when I fetch data from the memory to the cache is in blocks of 8 bytes. Okay, that means it will always start with the last 3 bits being 0 and the last 3 bits being 1. Okay, so it will start from 000 to 111, the last 3 bits. Okay, so the first memory access, okay, will point to cache index 0, cache set 0, and since the first block is empty, I will occupy the first block, so I'll update the valid bit tag information 0, and I will fetch the data from memory 0 all the way to memory 7. So the first word will start from memory address 0, and the second word will start from memory address 4. Okay, so that is the full 8 bytes for this memory access. Okay, memory address 4. Okay, so this is a common mistake that some students will make, where they say that when I say memory access 4, they will say 8 bytes starting from 4. No, so you must always see that every memory access belongs to an 8 byte block. Okay, and the 8 byte block basically you just need to make the last 3 bits start from 0 and go all the way to 111. Okay, that is where you get the starting and ending address of where this memory access belongs to, which block it belongs to. Okay, so that is your first access. Okay, now let's look at your second access. So again, the same thing. Now the second access is pointing to index 2. Okay, so again, I change the valid bit, set the tag information, and this is memory 16 and memory 20. Okay, again, in both these cases, the initial access is a miss. Okay, so you just update the data into the cache. Okay, the third access. Okay, so this is interesting because this is where you can see it points back to cache set 0. Okay, so in cache set 0, you can see that currently the first block is occupied, okay, but the second block is available. Okay, so because of this, I am now able to keep this information. So I change the valid bit, change the tag information to 1, and this is memory address 32 and memory 36. Okay, so you can see that this is where the set associative, okay, plays a part. Okay, why? I have two memory accesses, just now memory access 4 and now memory access 32, both point back to the same cache set. Okay, but they have different tag information. Okay, so same cache set but different tag information, and I can keep them side by side. So you can imagine that if I were to have a loop, okay, so for example, if I have a loop, okay, where I'm continuously accessing memory 4 and memory 32, okay, one after another. If this was a direct map cache and they both happen to map to the same cache line, then this would have been a continuous miss. Okay, because each time I would have to replace the cache line. Okay, but since it is a set associative cache, I can keep both of this data side by side, and only the first access in the loop would have been a miss, subsequent access would have been a hit. Okay, so that is where this set associative cache actually plays a huge part as being helping us in the performance. Now let's look at the fourth access. So the fourth access is memory address 20, and what do you see? This memory address 20 was already fetched when I was fetching memory address 16. Okay, so it's a hit, but this is nothing to do with set associative. Okay, this is because I have two words, okay, per cache access. Okay, so this is your spatial locality. Okay, so by increasing the number of words per cache line, I'm able to increase my spatial locality hits. Okay, so that is why when I fetch 16, I also fetch the word starting at 20. So the next time when I was trying to access 20, there was a hit. Okay, so this hit is because of the spatial locality. Okay, so if you carry on with the rest of the exercise, you can be able to figure it out. Okay, so this is the final contents of the cache. Basically what I want to highlight is the replacement policy. So the replacement policy is basically if you recall, is LRU, which is least recently used. Okay, so the easiest way to determine this is to just think of it as a timestamp with just two numbers. Okay, 1 and 2. 1 is the earlier access, 2 is the later access. A higher number is later access. So imagine that I initially updated cache line 1, okay, cache line 0 here with this memory 0, memory 4. So I put this at timestamp 1. Then this data came in, memory 32, memory 36. So I put a timestamp 2. Okay, and after that, what happened? After that, I had another memory access for 68, which was also going to map to this cache set. Okay, so one of this has to go. So the earlier one, which is the lower number, has to go. So this one will go, and this will become the new older one, and this will become the new later one. Okay, so similarly, when the memory access for 224 comes in, again one of this has to go, and this is the newer one, this is the older one, so this one will go, and this will be 1, and this will be 2. Okay, so you can just think of it as a timestamp with just two different numbers. Okay, in this case only two numbers because I only have two blocks per cache set. Okay, so I just need to figure out who is the later data and who is the earlier data. Okay, and from there I know who to replace. Okay, so that is the how the replacement policy works here. Okay, so basically this slide shows you the final contents of the cache, which you should be able to also get a similar answer if you work through all the accesses. Okay, let's go on to the last question, which is on palindrome checking. Palindrome checking is basically you are trying to a palindrome is basically a string, okay, of characters where you look at it from left to right or right to left, you sort of spell it the same way. Okay, so that is what you call a palindrome. Okay, if you go through the C code and the equivalent MIPS code here, you should be able to figure out what we're trying to do. Okay, so what I will just quickly highlight is you can see over here that this is where we are checking. Okay, and the S0 and S1 are basically the pointers. So S0 is pointing to the starting of the array, and S1 is pointing to the end of the array. Okay, and the data is then passed on to T2. Let me see, yeah, T2 here and T4. Okay, and basically the point where I check is line 11. So in line 11, after I load the data from both this into T2 and T4, I check. So if it's a palindrome, I will take the branch to else, which is line 11. Okay, so basically I start, okay, from line 1, correct, all the way to here. Okay, okay, and if it is a palindrome, I will jump to instruction 14, increment S0 S1. That means if it's a palindrome, then I must still carry on checking. So I move my S0 and decrement my S1, and again I do the same thing, load to T2, load to T4, which is everything here. Okay, and all of that is in the loop, so the loop goes back to I4. Okay, so if you analyze the code, you see I start from instruction 1, go to instruction 11. If it's a palindrome, I go to instruction 14. Then from instruction 16, subsequent iterations of the loop just go back to instruction 4. Okay, so that is how the code is written. You can analyze that. Now, in this question, you are first talking about this idea called instruction cache. Okay, so the instruction cache principle is the same as the data cache. Okay, so just like how data has spatial locality or the temporal locality, instructions also have the similar principle. So there's also a high chance that I will be fetching instructions. When I fetch an instruction, I may be fetching instructions that are also nearby each other. Okay, so it also makes the sense to keep some instruction in cache, okay, to minimize my external access to the instruction memory. Okay, so here we are given that the instruction cache has two blocks and 16 bytes each. So one instruction is 4 bytes, so I can have a total of 4 instructions per cache line. Okay, so we are given that when I fetch instruction 1, it is a miss, and subsequently 2 and 3 are a hit. Okay, so let's trace through the sequence. So the very first access for instruction 1 will be a miss, 2 and 3 will be a hit. Okay, and from 3 I go on to 4. So again, when I fetch 4, I fetch 4 to 7. So 4 will be a miss, 5, 6, 7 will be a hit. When I fetch 8, it will be 8 to 11. So 8 will be a miss, 9, 10, 11 will be a hit. After 11, I jump to 14. Okay, but again, you have to remember everything is in blocks of 4 instructions. So 14 belongs to the block starting from 12, ending at 15. Okay, so I still have to fetch from 12 to 15, and 14 will be a miss, 15 will be a hit. And similarly, 16 is also belonging to a new block. So 16 will be a miss, okay, because it's the start of a new 4 instruction block. Okay, so subsequently, if you recall, after instruction 16, I go back to instruction 4. Okay, I don't go back to instruction 1. The loop goes back to instruction 4. So if I look at the whole sequence, the first iteration is from 1 all the way to 11, then 14 to 16, and from 16 I jump back to instruction 4. So the second iteration onwards is instruction 4 to instruction 16. Okay, so if I count the number of hits, okay, so you can see that I have a total of 9 hits for the first iteration, okay, and subsequently 7 hits for the remaining iterations. Okay, total of 72 hits. So that is how your instruction cache actually helps to improve the performance of this piece of code over here. Now let's look at the data cache. The data cache we are given is a direct map cache with 2 cache blocks. Okay, and each block is 8 bytes. Okay, so since it's 8 bytes, you have a 3-bit offset, and since I have only 2 cache lines, it's only 1-bit index. So index 0, index 1, and in each cache block I have 8 bytes. Okay, so what is the final content of data cache? Now let's look at the whole sequence here. So when I am checking this data, so you imagine that I'm total is 64 bytes. So initially I'm going to check byte 0 with byte 63. Okay, and since my cache line is 8 bytes, when I fetch byte 0, I'm going to be fetching byte 0, 1, 2 all the way to 7. Similarly, when I fetch byte 63, I'll be fetching 63 down to 63, 62 down to 56. Okay, so again, you have to remember that the entire memory chunk is now broken up into blocks of 8 bytes. So whenever I fetch any byte, I must see which 8-byte block it belongs to. Okay, so 0 belongs to the block of 0 to 7, and 63 belongs to the block of 56 to 63. Okay, so now when I analyze in terms of the cache line, you can see that the byte 0 to byte 7 access map to cache line 0, while byte 56 to 63 map to cache line 1. Okay, and so what does that mean? So in the first time when I do a load byte, this will be a miss, and this will be a miss. Okay, and after I do the first check, what will happen? If you recall my code, I will increment my pointer to point to 1 and decrement my pointer here to point to 62. And when that happens, you will see that this data is already in the cache. Correct? So the remaining 7 accesses, okay, all the way, will always be a hit. Only the first one will be a miss. Okay, for this first 8 bytes. But what about the next 8 bytes? For the next 8 bytes, you will see that the cache line gets swapped. Okay, so the byte 8 to byte 15 is coming here. Okay, so 8, 9 all the way to 15, and 48, 55 down to 48 is coming here. So it doesn't matter if the cache line gets swapped, because what is important is for the entire 8 bytes access, I stick to the same cache line, and they are different cache lines. So again, the same thing, when I fetch byte 8, it will be a miss. When I fetch byte 55 will be a miss. Subsequently, everything else will be a hit. Okay, everything else will be a hit. So you can see that this pattern repeats itself again and again. Okay, so again I swap back. Okay, but again doesn't matter because the first access will be a miss. Subsequent access, 7 accesses will be a hit. Okay, and in the last uh, update of the cache, this is how my cache will look like. Okay, so you can see that with this data arrangement, okay, for every byte access, I fetching the next a full 8-byte block, and the first one is a miss, and the remaining 7 are a hit. Okay, so because of this, my hit rate is 7 out of 8. Okay, for every access, so it is 87.5%, which is very high. Okay, now in the next part, we are told that the string is now 72 characters long and it's still a palindrome. So if it's 72 characters long, what are we going to do? Okay, so if you look at it, again the same thing, except that now I'm starting from 0 and going to start ending at 71. Okay, so when I fetch the first byte to check, I will then check the byte 71. Okay, and if you look at the 8-byte boundaries, byte 0 again start from 0 and at 7, and sorry, this is 71 here. When we fetch byte 71, we will fetch bytes from 64 to 71. Okay, and interestingly, what you will see is both of them map to cache line 0. Both of them map to cache line 0, which means what? When I initially execute the instruction load byte for this byte 0, I will have 0, 1, 2 all the way to 7 here, and this is a miss, correct? And after that, I have another load byte for byte 71. So 71, 70 all the way down to 64. And this will also be a miss. Okay, because I have to replace this cache line now. Okay, and because I replace the cache line, okay, what happens? 1 to 7 also were replaced. So when I move on to the next index 1, I have to reload the cache line. Correct, so it will be a miss. And similarly, when I go down to 70, I have to reload the cache line, so again it will be a miss. Okay, since both of them are pointing to the same cache line, every time I access a new byte, I have to do a full replacement of the cache line, which means I'm going to have a 100% miss. Okay, can you see I'm going to have a 100% miss? Okay, because every byte is going to replace the entire cache line. Okay, so again, the same thing happens for the next 8 bytes. Okay, so byte 8 to 15 and 63 down to 56. Again, both map to the same cache line 1. Okay, so again, I'm going to have a full 100% miss. Okay, so you can work through the rest, okay, and see that the same pattern keeps repeating itself. Okay, and the only time where you actually get to have some hit is when I look at the last 8-byte block, which is 32 to 39. Okay, so you have to remember that this check with this, this check with this check with this, and this check with this. Okay, and only this last block here, 32 to 39, okay, is where I'm actually having uh, a point of time where I don't need to replace the cache line because all the data is within this 8-byte block. Okay, so effectively only this last 8-byte access, the first one is a miss. Okay, the first one is a miss and the rest are all hits. Okay, so only the last 7 are hits, which is for this block 32 to 39. So 7 out of the total 72 access, which is 9.72%. So you can see the hit rate is very, very low with just a small change of your string size. Okay, of course, one of the easiest way to solve this is to replace the direct map cache with a set associative cache. So you can imagine that if I had a set associative cache, then I would have been able to store this data over here. Okay, then both of them can be concurrently accessed in the cache at the same time. Okay, so having a set associative cache helps us in situations like this where two different memory access with the same cache line can still be kept together. Okay, and this is also interesting, this question, because you can see that with the same code, if you look back to the code, with the same code that you have, okay, which is this palindrome checking code, all I did was change the size of my array, correct? And suddenly the performance just drastically changed. Okay, so this gives you some idea on why sometimes, when you are writing some code, the performance of the code in terms of how efficiently it was executing, in terms of the speed, can suddenly just change the moment you change the data structure, or the way you rearrange the data from maybe a 1D array to a 2D array or something like that. Okay, because it could be a situation where suddenly the way the data arranged was very much in line with how the cache was designed, or suddenly it was very much against the cache design. Okay, so you could see some sudden swing in performance with the code being the same, but just the way the data was organized was different. Okay, so again, it gives you some idea on why this module is important, because when you have a deeper understanding of the hardware, okay, that you are dealing with, then it makes you a better a software developer, okay, in terms of developing solutions and applications. Okay, so that brings us to the end of this tutorial. In the next video that I'll be releasing soon, we will talk about this week's tutorial on Boolean algebra. Okay, so thank you.